Swayam Prabha. Digital India. Educated India.
Hello and welcome to this week's lecture on MDPs, Markov decision problems. So we're making the switch this week from Bandits, which we did for the first 3 weeks, to MDPs. Okay, and in a slight departure from what we did last time. So remember that last time I introduced the topic to you by playing a game, sort of giving you like some intuition, and thereafter we followed up with the mathematical formulation. I'm going to do it the other way around this time. Okay, so we're going to introduce MDPs as a mathematical object, and you see that farther down, right? In one of the sections in today's this week's lecture, we will actually look at real-world embeddings of this abstraction. So here's what's lined up for this week: defining the key concepts. What is an MDP? What is a policy? What's a value function? And thereafter formalizing what is the problem that we're going to solve with MDPs. Okay, that's called the MDP planning problem. Thereafter, I will mention some variations of this problem. Okay, so this is a fairly old established topic. It's been around for 60, 70, 80 years maybe. I mean, right after the Second World War, when dynamic programming and operations research was developed, right? MDPs are a byproduct of that. And so in the literature, you will find multiple definitions. Okay, so one of the things I want to do today is, of course, give you the one that we will be using, but also tell you that's not the last word. There are some variations that you might encounter. We look at some applications and just get started. Okay, so in section 5, we will do something called policy evaluation, which is really the first step towards solving the problem of MDP planning. Okay, all right, so let's get started with section 1, which is just definitions. So the fact that it's a definition does not mean it's got to be verbose in text. You can actually get a good idea of what an MDP is by looking at this picture. Okay, so this is a particular example of an MDP. I mean, what really does an MDP have, right? So let's go through that list in this first few minutes. So an MDP has 5 elements. Okay, it's got S, A, T, R, and gamma. Okay, so now I'm going to tell you what each of those things is. So S is a set of states. Okay, so as you can see from the figure, it looks like what most of us will call a state transition diagram, right? So the set of states S in this MDP is S1, S2, and S3. There are 3 states shown as circles, blue in color. So more generally, right, for our discourse, let's assume that the set of states is S1, S2 through Sn, which means n is the number of states. Okay, and at least for now, we are going to assume that n is a finite number. All right, so an MDP has a set of states. It has a set of actions. Okay, A is a set of actions. This particular MDP has 2 actions. Okay, it's got a red action and a blue action. So an action is something that an agent can take from a state. Okay, so if it is an S1, it can take red or blue. From S2, it can take red or blue. From S3, it can take red or blue. In general, you can have more than 2 actions. You can have K actions. Okay, so we'll assume that the number of actions is K. The actions themselves are A1 through AK. Of course, here K equal to 2. And let's say A1 is red and A2 is blue. So what's going on, right? What are we going to do with these states and actions? That is what is represented in what is called the transition function of an MDP. So that is denoted T. So a transition function takes in 2 arguments. Okay, it takes in a state and an action, and what it gives as an output is a probability distribution over states again. Okay, so given an S and an A, it will give you a next state distribution. Okay. So let's look at that somewhat more formally and also with an example. So maybe we'll do the example first. So the meaning of drawing the picture like this here, right, means if from state S1, if the agent takes action red, okay, then you see that there are 2 outgoing arrows colored red from S1. What's annotating these arrows, right? What's written on each arrow is a transition probability along with something called a reward. Okay, that's what we'll see next. But the transition probability here is 0.5. transition probability here is 0.5. Right? That means the transition function gives a probability half of remaining S1 if action red is taken, and allots the remaining probability to going to S2, and allots zero probability of going from S1 to S3 by taking action red. Okay. Similarly for blue, it turns out the probability distribution of S1 comma blue puts all the mass on just one state, right? And that is S1 itself. Okay, there's no probability of going from S1 to S2 or S3 by taking action blue. And you can see similar probabilities associated with the other state action pairs. All this is encapsulated in what is called the transition function. It's called a function because it takes in state and action as input and gives probability distribution over next state as output. Or if you want, you can give S prime as input, and the output is a probability, okay, of going from S to S prime by taking action A. Also part of an MDP is the reward function R. Okay, so you've already seen that these arrows are annotated with transition probability comma reward. So what I mean by that is, for every transition, right? A transition is triple. Okay, it's a state, an action, and a next state. The transition probability, the transition function gave the probability, right? The reward function associates each such triple with a numeric reward. Okay, so it's a number. All right. So what it means is, if you go from S1 to S2 by taking action red, the transition, of course, will happen only with probability half. But when it happens, the reward that the agent will get is -1. Okay, and the reward that you get by taking action blue from S3 is 1, okay, because it's always going to go to S1, and that transition has a reward of +1. So we'll assume that rewards are going to come from some bounded interval. The convention is to say that they are going from, they're bounded within R max from 0. Okay, there's some number R max that's greater than or equal to 0, and the rewards are all coming from minus R max through R max. Okay, so technically, I mean, if you're a stickler for rules, you can say R max is also a part of the MDP's definition, but sometimes you just don't make it explicit. All right. Okay, so this is what we have seen depicted on the picture that we have drawn. Okay, a set of states, a set of actions, a transition function, a reward function. So what we've not specified yet is this thing called the discount factor gamma. Okay, so gamma is going to be a number. What that number is and why we need it, it's too early to be telling you. So hold on. I don't know, 10 minutes from now you will encounter a definition of gamma. Okay, so wait for that. All right, so let's go forward and see what is going to happen with an MDP. We defined an MDP, but then the idea is we are going to do something with it, right? So an MDP is a way of representing the interaction that goes on between an agent and an environment. Okay, and this happens over time. Okay, so the most important aspect of an MDP, which didn't actually come in the definition of an MDP, but which is the whole reason it is there, is the fact that time happens, time elapses. Okay, and things happen over time. In particular, if there's an agent that is living, it has to do something, right? It's called an agent because it has agency. Its job is to take actions. And an MDP describes what happens when an agent takes actions. So let's go through, right, step by step what this interaction is. So when we just initialize, right, let's take t equal to 0. Then the agent finds itself in some state. Okay, let's call that state S0. And using the same convention as we had with Bandits, when we say S superscript 0, that 0 there stands for time. Okay. Now the agent is in some state and it has to take an action. Okay, an agent's job at any point of time is to take actions. So let's say it takes action A0. So in our example, that might be either red or blue. Once the agent has taken an action, the environment now generates a next state S1 as well as reward R0. Okay, so in particular, the next state is drawn from the probability distribution T of S0, A0. Okay, the transition function is invoked, passing S0 and A0 as inputs, and therefore there's a distribution over next states. S1 is sampled from that. All right, And once S1 is fixed, right, you can also get the reward for S0, A0, S1. Again, that's given by the environment. And this is given back to the agent. Just a matter of convention, in some places you might find the reward that is being generated as a consequence of S0 and A0 denoted R1, okay, because the reward also depends on S1. So we will go with the convention that the reward is going to still be called R0. Let's just take it as the reward that you got for what you did at time step 0, all right, which was taking action A0 from state S0. Anyway, now that this one atom of interaction has happened, time progresses by 1, time becomes 1, agent is now in state S1, okay, where it reached after doing A0 from S0. And in state S1, the agent again has to take an action. Let's say it takes action A1, and in response, the environment will generate S2 and reward R1. And this process goes on, okay? It goes on for ever. And therefore, right, it is convenient to summarize the agent-environment interaction simply as a sequence: state, action, reward, state, action, reward, state, action, reward, all the way, okay? Each state, action, reward at some time step, then state, action, reward at the next time step, etc. Okay. All right. So let's view the same thing using another schematic. So here you see the agent environment interaction as just a sort of feedback cycle. So from state ST, the agent takes action AT, okay, at time step T, and then the environment comes back to the agent with reward and the next state. And again, this agent will take action, time having gone up by 1, and then the agent environment loops back. Okay, so this will keep happening. The key question, all right, is on what basis does the agent pick its action, right? How did it decide to pick either red or blue, right? How did it pick AT? Now, in the most general sense, right, an agent, what it can do is it can basically remember everything it has seen so far, right? It can remember its entire history, which is up to time t, right? All the interactions, state 0, A0, R0, S1, A1, R1, right through state t. And we can look at this history and decide which action to take, all right? However, for now, okay, let's assume that the agent is doing something simpler, and the agent is actually deciding which action to take purely by looking at the current state. Okay, so the agent is in state ST. Let's say that the way it picks AT is simply as a function of ST. Okay, it really doesn't look at what has happened in the time steps 0 through t minus 1 to get it to ST. It ignores all that information, but given ST, it takes an action AT, let us say. Okay, if that's what the agent is doing, then we can describe this technically as the agent following what's called a policy. So a policy, formally, or rather the way we are formalizing it, is a mapping from states to actions. Okay, so given a state, if you apply a policy to that, that will give you an action. Okay, for every state, a policy pi will specify which action to take. And by virtue of defining it in that way, we are defining a policy to be Markovian. Okay, so Markovian means you're looking only at your current state, you're not looking at anything that happened before. We are defining our policy to be deterministic in the sense that from your current state, the policy specifies a single action. In principle, you could have a stochastic policy too, right? A policy that, even if it is Markovian, let's say looks at your current state and gives a distribution over actions. That's a very legitimate way of defining policies, although we have not defined it like that. The third defining attribute of our policy is that it is stationary. Okay, so the policy doesn't actually depend on time. So it's a mapping from states to actions, right? So whether you're in a particular state at time 0 or 25 or 312, if you're following a policy, you will take the same action, okay, because the state is the same. In general, a policy could also be non-stationary. Okay, it depends on history, at least to the extent that it needs to know how long the history is. Okay, so why did we define our policy to be Markovian, deterministic, and stationary? We needn't have. It suffices for our purposes. Okay, as we go forward within the next few slides, you will see that this definition is enough for the purposes that we are going to use policies right now. Farther downstream in the course, right, we might relax some of these assumptions, but for now, right, when we say policy, assume that it is a mapping from states to actions, and therefore it is Markovian, deterministic, and stationary. That's what we mean when we say policy. Okay, so let's build some more familiarity with policies. Again, looking at our illustrative MDP. So this had 3 states and 2 actions. Here is one particular policy for this MDP. Okay, so here is a policy pi, which takes action red at state S1, which takes action red at state S2, and which takes action blue at state S3. Okay, so this is one particular mapping from states to actions, right? And that is what this policy pi is. Okay, now if that is what pi is, what really does it mean to follow pi, right? When an agent is implementing or following pi, what really is going to happen? So let's assume that the agent is actually starting at state S1. So by following pi, right, it means the agent is going to take action red. When it is in S1, it's going to take action red. So what can happen as a consequence? Well, as a consequence, either the agent stays in S1, because with probability half that's going to happen. With the other probability half, it can go to S2. So even if the agent follows a fixed policy, right, because the world is stochastic, transitions are stochastic, different trajectories can happen, right? So here are a couple of examples of what can happen when the agent follows policy pi, right? From S1, it will take red. Well, maybe it's stayed in S1 even for the next time step. Again, it took red. It went to S2. So notice that whenever the agent is in S1, if it's following pi, it has to take red. Okay. So in any of these trajectories, you will see that the action following S1 is always red. The action following S2 is always red. The action following S3 is always blue. That's what it means to be following pi. But that doesn't mean the same trajectory is going to happen, because although the agent took red, right, one time it stayed in S1, the other time it went to S2, right? And similarly, from S2, right, it took red, went to S3, from where it took a blue, right? But here what happened, from S2, it took a red and went to S1. So because of the randomness in the environment, right, the trajectories that are generated can be different, but both of these trajectories are possible consequences of following policy pi starting at state S1. Okay, so I think it's worth emphasizing the following point. A number of when you're seeing this for the first time, a number of people will think of the agent as deciding to do something like, I am going to S2 from S1, or I am going to S3, right? Now, that is not allowed in the model that we are considering. All we are allowing an agent to specify is which action it is going to take. That's fully in the agent's control, right? So a policy is basically what resides in the agent's control, in its agency. And so it can specify which action. If actions happen to be deterministic, right? For example, if take the blue action from S1, right? In fact, blue action from any of these states, I think, is a deterministic action, in the sense that if you take that action, your next state is fixed with probability 1. So maybe instead of saying I'm taking blue from S3, right, you can say something like I'm going to S1, right? Because you know that it's going to happen. But that's a very, very peculiar aspect of this MDP, right? In general, we allow MDPs to have stochastic transitions. And therefore, all an agent can say is, I want to take this action, which is what it's saying by specifying its policy. But where it reaches as a result of that action, that resides with the environment. Okay, and we know that that's happening according to a random process. Okay, so good. So even if you have a fixed policy, you can have multiple trajectories starting from the same state. So let's now go a little bit more into understanding policies. In fact, the one that we saw, right, pi, which took red at S1, red at S2, red at blue at S3, I mean, is not the only policy, right? There can also be other policies applied to this same MDP. So let capital pi, okay, capital pi is this funny looking thing. It's pi, okay, written in capital letters in Greek. Let that denote the set of all policies, okay. So the natural question is, what is capital pi? How many elements does capital pi have? Okay, so take a minute to think about that. I've shown you one policy which was red, and blue. How many other such policies can you have? Okay, so on this particular MDP, you can do either red or blue at S1, either red or blue at S2, and either red or blue at S3, right? So the number of policies is 2 times 2 times 2. So more generally, if you have k actions and n states, the number of policies, by that, remember, I mean deterministic, Markovian, non-stationary policies. That number is k raised to n. Okay, so capital pi is a set of k to the n policies. So now the natural question for us to ask is, these are all policies, but which policy amongst these would I prefer, right? What is a good policy? What is not a good policy? So by now, I hope you've already built some intuition. We're calling these numbers, right, on the arrow. One is the transition probability, but the other is a reward, right? So reward sounds like something that you should try and have more of, okay? And I mean, a reward of -1 sometimes is called a penalty of 1, right? But if you just think of reward as a scalar, right, what we would like policies to do for us is to give us lots of reward, right? So now that's a little tricky for us to define, because who knows, right? A policy might take us from S1 to S2, let us say, and give us negative reward, right, for doing that. In fact, I think this policy does it, right? So if you take red from S1, you're getting a negative reward, but then it is taking you to S2, right? Who knows? From S2, maybe you can get a lot of reward, right? In fact, you're able to get a fair amount of reward by taking blue, right, starting at S2. So maybe red from S1 is not that bad, because it either keeps you here with 0 or it takes you to S2, but from S2, right, there is salvation in being able to choose another action and take another, get more reward, right? So essentially, we want policies that encapsulate the idea of what is called sequential decision making. You want to take decisions or actions that not only give you good one-step rewards, but maybe sometimes they sacrifice it, but in the future too, they must give you good rewards, okay? So this notion that we want to have a lot of aggregate reward along an entire trajectory, right, is what is captured in our definition of what is called the value of each state under some policy. So let's look at that definition. So for policy pi, and for each state S, let us define V pi of S simply to be the sum of the rewards. Okay, so the reward at time step 0 plus reward of time step 1 plus the reward of time step 2 forever. Okay, in expectation. Okay, when you are following pi, which means you're taking actions according to pi, starting at state S. Okay, so V pi of S, there's some state S. So let's assume that at time step 0, right, we are at that state, and then let's see what happens when you follow this policy, right? In expectation, right, what is the first reward plus the second reward plus the third reward forever. So that is the natural definition of what is the long-term value of following this policy starting at that state, right? So that's precisely what we are defining to be V pi of S. Well, not quite, for a simple reason. I mean, imagine that these rewards are all positive, right? Let's say they're all between 1 and 2 or something like that. This looks like an infinite sum, okay? R0 plus R1 plus R2. If that happens, then V is also going to be infinite, right? So a standard way of making sure that our semantics is captured, but we don't run into sort of mathematical difficulty, is to use what is called discounting, okay? So let gamma, see, this is the part of the MDP which we had not defined yet. So let gamma be a number between 0 and 1 excluded, okay? So formally, let us define value of state under policy pi to be R0 plus gamma times R1 plus gamma squared times R2, etc. All right. So this notation might be a little bit confusing. So the two superscript for gamma is gamma squared, right? And this is gamma cubed. Gamma is a scalar, right? And the superscript for r is the time step. Okay, this is time 0, time 1, time 2, etc. Gamma doesn't change with time. Okay, the reward changes with time. And so we can formalize this as our definition. It's not very hard to see that if gamma is less than 1, right, value has to be bounded. It cannot be infinity. In fact, values will have to lie between minus r max over 1 minus gamma and r max over 1 minus gamma, because each individual reward was bounded. The infinite sum is also going to be bounded to that scaled by 1 over 1 minus gamma. Okay. All right. So this slide looks like a reasonable definition of how good a policy is starting from a particular state. Again, something to emphasize for somebody seeing this for the first time. So gamma is a part of the MDP. Okay, it's given to us along with states, actions, transition function, reward function. In some sense, gamma is telling us what we should be optimizing for, right? I mean, ideally, we want values that are good in some sense, but that very definition of good, right, takes into account gamma, right? So if you change gamma, you're going to have a different definition of v pi of s, right? So what really is the semantics of gamma? So think about it. As you make gamma larger, right, more and more of your future rewards are going to come into the definition of v pi of s. They're going to influence it. I mean, the smallest value you can set gamma to be is 0, right? If you're taking gamma to be 0, then literally you're saying that the value of this policy is the one-step reward that it gives you, right, in expectation. You don't care what happens second time step onwards. It's a good policy if it gave you immediate gratification in some sense. On the other hand, as you make gamma larger and larger, I mean, you're really asking, right, where does this policy take me? What kind of rewards am I getting from there? Okay, so gamma is that sort of parameter that summarizes how much the future matters to you. Okay. Again, sometimes students are wondering, I mean, what is the right way to set gamma? That's a question you should be asking if you are the designer of this MDP. Okay, it's not a question that you should be asking if you are an agent, right, that has been given this MDP. Okay, if you're given the MDP, it means you're given gamma. You don't really have a choice of changing gamma or something like that. Okay, it's a part of the input. It's not something that the agent can independently control. Right? You'll see there are other things that the agent can control if it wants, but gamma is not one of them. Just to maybe give you another example to think about the meaning of gamma, right? So take the example of let's say you're given a box full of gulab jamuns, okay, 10 gulab jamuns or 12, right, whatever they pack and give to you. Will you eat all of them up right now, or will you not? Okay, so if you have a very small discount factor, right, let's say gamma equal to 0, maybe the right thing to do would be to gobble up 12 gulab jamuns, okay, because it's going to give you a great amount of immediate reward, right? A lot of sugar, right, feel good, energy to do things, and just that, I don't know, craving that is satisfied. But presumably you're going to go into a state which is not very desirable, right? It's not going to be I don't know, good for your stomach, right? Maybe in the long term, it's not good for all that fat to get accumulated in your body. So if you have a larger discount factor, right, you will not eat 12 gulab jamuns in one go. Okay, I'm not here to tell you whether you should eat those gulab jamuns or not eat those gulab jamuns. Okay, so I'm not going to tell you that gamma small is good, gamma large is good. Somebody has decided, okay, and it comes to you, and you have made your definition on the basis of what gamma was given to you. Okay, all right. So that was just an example. Okay, you can think of other examples from real life where you're asking the question. I mean, I'm thinking of doing this. Is it good for the short term? Is it good for the long term? Right? And this is often also the discussion that happens between different people. Right? Maybe you're talking to your parents, right? They tell you, don't do this, it's not good for your long term, for your career, for your future, right? They are invoking a large value of gamma, but you might be invoking a smaller value and just say, well, it makes me feel happy right now. Up to you, okay? I'm not getting in between you and your parents.